Okay, recording now.
So we're very happy to have Shashank back to give us his talk on completing the A2 Andrews-Schilling-Warnaar identities. So my uh, laptop camera doesn't work for some reason, but I'm here. So Shashank, please go ahead.
Okay, so this is joint work with Matthew, and um, it relates to all sorts of things like cylindric partitions and W algebras and all that. Uh, and this is sort of a long presentation. As I was making it, I realized it's a bit long, so I don't have to get through all of it, obviously. So I'd much rather that you stop me and we discuss and all that. Okay, so before I begin, Matthew already gave a talk on this work at a seminar called Speciality Seminar on Q Series by William Keith, who was a former student of George Andrews. And his talk is really very nicely organized, and I'm worried that my talk is a bit all over the place. Anyway, so if any of this piques your interest, definitely look at his talk. So the talk today is about principal characters. I'll explain what that means of standard modules for A21. And I have a non-trivial number of friends who, if I tell them that I'm working on integrable modules for affine Lie algebras, they'll immediately get put off. So I'll say that this is also related to W algebras and principal W algebras of type A. And really, when you're talking about A2, it is related to W3 algebras at certain parameters. So there is some really deep story about why all these things are related, and hopefully we'll get to that. I don't understand it fully. Anyway, so let's get some notation out of the way. This is the Pochhammer symbol, which you can think of as the rising factorial. And the only thing to remember here is that this J means there are J factors here. So you stop at J minus 1, you start at Q to the 0. And if you put A equal to Q, then you get Q to the 1 up to Q to the J. And this J could actually be infinity, in which case you just continue. And sometimes I need to multiply these Pochhammer symbols, so I just condense all that notation into one bit. I'll need another notation which is convenient. This is called modified theta function. So you often need these symmetric products where if you have A, then you also have Q divided by A, and that's this notation. And I'll also need Q binomials at some point. All right. Okay, so let's also get some notation about affine Lie algebras. G will typically stand for an affine Kac-Murray Lie algebra. And here is an example. If you have never seen one, this is the SLN hat. So that's the underlying vector space for it. And C is central. So you're taking your usual SLR and taking the Laurent polynomials whose coefficients are valued in SLR, and you're taking a central extension. I don't need the plus D, the derivative part that comes about from VOAs anyway as the L0 or minus of L0. So that's not important. And that's usually the bracket. So that's an example, but this is just one example. There are infinitely many such things there. Today, we'll just need these type A. That's really okay. So these will be the simple roots, alpha I. We'll also have the fundamental weights, lambda I, capital lambda I. And we'll have the usual notation for highest rate irreducible representations. I'll also call these standard modules. Oh, no, sorry. For standard, I will require these to be integrable. And the main object of study today would be the characters of these guys, which live here in this formal, I mean, up to a e to the lambda, it lives in a formal power series ring with these formal symbols. But really what I need is their principal specialization. So what you do is you remove this top guy. So you normalize them effectively, and you set all of the formal exponentials you see here to Q. And now you get a nice just formal power series in Q. Okay, later on, I'll actually talk about something called principal characters, which are a little bit more than principally specialized characters. It's an unfortunate, like, you run out of adjectives to put. So anyway, all right, I'll come to that when I come to that. Okay, so our story begins in late 70s, where Lepowski and Milner actually studied the principally specialized characters of some affine Lie algebras. And they found, for instance, for A11, that if you look at this principally specialized character, you get this very nice periodic product. And this +2 you can understand as the dual Coxeter number and so on. If you're familiar with these products, then besides this orange part, this black part is really the products in Gordon-Andrews identities, or Andrews-Brasseau identities, depending on whether your level is even or odd. And they also did this for A22. Now you get, instead of this 1 over QQ squared, you get this factor. And then you get some products which can be handled by quintuple product identity. Anyway, the point is this factor here, it's there in every integrable module, and it depends only on the Lie algebra that you're talking about. So it's a natural question to understand, like, what happens if I delete this and the real meat is here? Can we understand that? And this is exactly what Lepowski-Wilson did. They explained these types of factors. This is really the character of a principal Heisenberg subalgebra. And in the case where your affine Lie algebra essentially comes from type ADE, then this character is also the character of principally specialized character of the basic modules. And really the interesting bit is in the remaining stuff, which is the highest weight vectors with respect to this principal Heisenberg. Okay, so the real object of study for this talk today would be that remaining stuff, the highest weight vectors with respect to the Heisenberg. So you're really taking the principally specialized character and you're deleting this extra orange factor that I had in the previous slides. And I'll denote these by omega lambda. Omega stands for this vacuum spaces, as it's called. And this is what I'll call the principal character. Okay. Okay so far? All right. Okay, so at odd levels of SL2, you get these Andrews-Gordon identities. And these are the products that I showed you in the middle line. On the right-hand side, I'm showing the designation of which modules they come from. And on the sum side, there is this expression. Now, one thing to note is that I'll always assume that whenever you have such expressions, the Pochhammers in the denominator have non-negative things here, right? So it is assumed that the sum is over n1 greater than equal to n2, n2 greater than equal to n3, and nk greater than equal to 0. I'll not mention that. But there is a nice formula which is typical, which is q raised to a quadratic form plus some linear terms divided by Pochhammers. And I'll show you how it looks at even levels. This is how it looks at even levels. So I don't know if I just make a GIF out of it, then I don't know if you can tell the difference. But really the difference is only in this terminus, okay, the last variable nk. Nothing else really changes on the sum sides. And so what you can do is you can ask what happens if I take this k to infinity. Okay, so k is related to the level, right? The level is roughly 2k plus 1 or 2k. So you can take this level to infinity. And well, what's going to happen is on the right hand side, sorry, on the, on the right hand side, what's going to happen is when you take k to infinity, q raised to infinity is 0 in this, you can have this q-adic topology or whatever. And so really what's going to survive is only this factor 1 minus q to the I. Everything else is infinite, so it disappears. So here on the product side, you would get something like 1 minus q to the I divided by a q infinity. And on the left-hand side, you'll get an infinite fold sum, okay? So this is how it looks like on the left-hand side. This is an infinite fold sum. On the right-hand side, this is what you have. That's the product. And really, I'm taking the level to infinity. So this is infinite times lambda 0. Okay, well, whatever, right? But the way I understand it really is, I think of this as really the principal character of generalized Verma modules, because what is happening really is that in generalized Verma modules, what they are is you take an irreducible module of SL2 and you induce it up parabolically to a module for SL2 hat. And by sending the level to infinity, what's happening is that you have this top irreducible guy at the top of your module, and the affine singular vector x theta minus 1 raised to k plus 1 or whatever it is, that gets pushed down to infinity. So really, you have a very free part on the top, except for the irreducible module up there, and then it's sort of free. So so I think the way to understand this is via generalized Verma modules. So you're getting character formulas for such modules. So okay, so there is another thing you can do. You can also send this I to infinity, right? So then you are taking infinite lambda 0 plus infinite lambda 1. And then all this linear terms will also disappear, and you'll just get q to a quadratic divided by Pochhammer's. And on the right-hand side, you'll just get 1 over q to the infinity. So this is all you can do. And so for finite values of I, I'll understand it as principal characters of generalized Verma modules. And for an infinite I will just understand it as principal character of Verma module. And level doesn't matter, because at the end of the day, we are just normalizing all these characters anyway by deleting that e to the lambda. So the level is not going to matter at all. Okay, sounds pretty weird, but let's keep going. So there is this Garland-Lepowski resolution of integrable modules in terms of generalized Verma modules. And for SL2 hat, this resolution has just one single Verma module at every step of this resolution. So you can immediately ask a question, and I don't know how easy that is, that for the integrable modules which sit at the very end, you have these finite fold sums. Like if the level is 2k, then you have roughly k variables or something like that in the sum. But each of these guys has an infinite fold sum. So if you look at the Euler-Poincare character of this sequence, then somehow these infinite fold sums close up, and after adding and subtracting, you get this finite form as the character of this integrable module. And I really don't know how that works. The point is that I'll show you the story for SL3 hat in a moment. And in principle, if one could understand here at SL2, then there is probably some hope of doing that for SL3, and you might be discovering some really new things there. But anyway, probably this was a bit fast, but so let me ask, are there any questions at this point? Because after this, I'll go to SL3. I don't really see the chat, so if you have a question, just shout out. Okay, so let me go ahead. In summary, for SL2 hat, we understand sum size for principal characters of standard modules. And we understand how in the limit they give rise to generalized Verma modules. What we don't understand is how to go back. And this is sort of a nice story. Like you first understand integrable modules, you take the limit, you understand Verma modules or generalized Verma modules. And potentially you could even then understand characters for like non-integrable modules where you have such resolutions, like admissible but non-integrable levels. Anyway, but that's a pipe dream. Okay, so this is a big industry of finding out these types of identities related to affine Lie algebras and their integrable modules. So obviously you can ask what happens for the next rank up, like A to 1 and even higher rank. And let me just give you the summary of what we do know at this point. So for A to 1, at the moment with Matthew, we have conjectures for all standard modules, how the sum size should look like. We also have conjectures for these infinite level or alternately generalized Verma module characters. And already a lot of special cases were known. I mean, the whole story starts with a really groundbreaking paper of Andrews-Schilling-Warnaar from 1999. And it was published in JAMS. So you can already see how big and important that paper was. And recently, there have been other special cases known by Cortil Welch, Cortil Duse, and Unju, Warner himself, and now by us. And none of this story really is known for any higher rank besides A21, which is kind of interesting. Warner has conjectural sum sites for infinite level case, but we don't know how to truncate them to get finite level identities, which is why I mentioned that I don't even understand in SL2 how to go from, anyway, yeah, that's what I mentioned in the SL2 story. Okay, so what did Andrews-Schilling-Warnaar really do? What they did was so there is this big theory of Bailey pairs, which is a very classical story starting from the work of Rogers, so more than 100 years ago. But I mean, of course, it was implicit in his work, but Bailey was the one who actually understood that there is this machinery of Bailey pairs and all that. So Andrews-Schilling and Warnaar defined A2 generalizations of A1 Bailey pairs. So the classical Bailey pairs are A1 Bailey pairs, and they invented an analog of the A1 Bailey lemma. So what it does is, starting with an A2 Bailey pair, you transform and get a new A2 Bailey pair. So I should mention that the A1 Bailey pairs have been incredibly useful in understanding characters of various things that are essentially rank 1 phenomena. Like you can understand SL2 characters, Virasoro characters, n equal to 1, super Virasoro characters, and they all really somehow fall down to the A1 Bailey lemma because they are sort of rank 1 phenomena, or affine rank 2 if you want to count the affine node. But anyway, so they did A2. And okay,
Shashank, what is the representation theory meaning of the Bailey lemma? I think I asked you this question.
Yes. So how about I ramble about it at the end of the talk?
Okay, sounds good.
Yeah.
Thanks. Yeah.
Yeah. I don't understand it fully, but I will say what I do know. Okay. So some things to remember in this. So remember, for SL2, we had this odd and even levels. Odd levels gave Andrews-Gordon, even levels gave Andrews-Brassus. So it's like a periodic mod 2. And in A21, you can expect this to be periodic mod 3. So levels are really grouped in groups of 3. And turns out that levels which are 1 mod 3 are somehow most straightforward. They fall right out of the Bailey lemma, like level 4, 7, 10, and so on. Then you have to sort of dualize the Bailey pairs and get 3k minus 1. And 3k is somehow independent. You have to completely get a new Bailey pair and analyze those. So really, the way the counting goes is you do 4, 2, 3, then 7, 5, 6, and 10, 8, 9, and so on. Let me just show you how these identities look like. So for Andrews-Schilling-Warnaar, they figured out some identities at every level, not all of them. So this is level 7 modulus 10 identity that they have. And okay, if you've never seen things like this before, then your eyes would glaze over it. But I would like to point out certain things. Like this quadratic form that you see here is really coming from the Cartan matrix of A2. You're doing the vector R1 S1, you're pairing with that. I mean, you're doing the inner product with respect to the Cartan matrix and dividing by half. And that's also you're seeing here. And as I said, you have quadratic terms usually in the numerator, and sorry, in the exponent of the q in the numerator. And then there are some linear terms like this R1, R2, and so on. And at the bottom, you have two pairs of, I mean, there are two strings of variables here, R1, R2, and S1, S2. At the bottom, they are largely independent. You have R1s just playing amongst themselves, S1s playing amongst themselves, except that at the end, there is a terminus where R2 and S2 sort of are linked together. So at higher levels, this is what you have. You have a link of R's, a link of S's, and at the end, they link up with a terminus. And this is the character up to this annoying factor, which I'll talk about at the end, 1 over q infinity times this principal character of this level 7 module. Now, as I said, level 8 is very similar, but you have to dualize something. So what happens is just the quadratic form for the last terminal variables changes. You get a plus here in between. And the next thing in this shelf of mod 10.8 is the 9. And here, what changes is this linkage amongst the very last pair of variables. So this is you have to put a QQ binomial, and this linkage changes, but the rest of the stuff is all the same. Okay, so this is how it goes up in shelves of 3. Right, so they discovered all this using their Bailey lemma, A2 Bailey lemma, I should say. So if I actually write down the mod, let's take an example. Let's look at level 16, and let's write down all the standard modules that you have at this level. Then Matthew and I realized that this is the correct way to arrange them in this triangular shape. And what Andrews-Schilling-Warnaar found out were some sites for this diagonal here, and then a couple of isolated cases down here. Okay, so I think this arrangement is also equally important as all the theorems we have proved in my paper with Matthew. It really tells you how these identities are going to look like if you try to fill in these things. So I'll now tell you what we figured out. One is, firstly, there is this, so you see in this triangle, there is the number of modules is sort of increasing up to some point, and then there is this line, and then the triangle sort of starts receding down. So we are able to give explicit conjectures for all the guys above this line, and they really come from truncating infinite level conjecture. So you take an infinite fold sum and truncate it nicely. Then we show that the bottom ones, they don't really have nice, good explicit formulas, but they can be deduced from the guys above. So once you know the picture above, the picture below is sort of determined. So this is pretty much what we have been able to do, and we have proved our conjectures for level 7 mod 10, which has been a new thing. Some earlier levels were known, but not that level. All right, so this is what I explained to you. At every level, we have explicit conjectures above the line. These are truncations of infinite level conjectures, and identities for modules below the line are determined by what are called Cortile-Welch recursions for cylindric partitions. And at levels divisible by 3, explicit forms of below the lines are known by some other circle of ideas using an identity of Weierstrass. And this 3 is interesting. It's the dual Coxeter number. So things always go wrong when you are divisible by that, or really if you have a factor common with that. At, again, levels divisible by 3, we have some new sum and product identities using this identity of Weierstrass. And certain new identities were found at level 3 and 7. Levels 2, 4, 5 were known because of the works of others. And curiously, level 6 still remains. So usually these levels, which are divisible by 3, they end up being sort of weirder, and that's probably the reason why level 6 is still remaining. We just couldn't make our methods work for that. Okay, so let me spend a moment on this infinite level part. So in infinite level, I'm taking this coefficient of lambda 0 to be infinite, and you should really understand it as taking an infinite level limit. It's not really setting anything equal to infinity. And our triangular picture then has no horizontal line. These modules just keep going down, and this triangle just keeps increasing as you go down. And again, you should view these as generalized Verma modules induced from this finite dimensional SL2 module, SL3 module, I'm sorry. Okay, so as I promised, these look like infinite fold sums, and now there is no linkage between the R and S. The R's and S are largely independent at the bottom, but on the top they are, oh, this should be an R1 squared and R2 squared. At the top, they are paired up with this Cartan inner product. There is also this 1 minus q that's an artifact of this sort of a limiting process. But anyway, so there are these identities corresponding to this this sort of vacuum generalized Verma module, where you are inducing it from the trivial SL3 module, and that's the principal character of it. So again, principal character means you take the character, principal is specialized, divide by the character of the basic module. So Warnaar had proved this identity in his recent paper, and he has effectively also proved the identity corresponding to other infinite limits, where you take everything to infinity or one of them to infinity and so on. So again, let me remind you that our conjectures above the line, they come from truncating this infinite level picture. So we have conjectures at infinite level for everything in the triangle. And for example, this is how it would look like if you are looking at this thing, this module, for instance. And it's a nice difference of these infinite fold sums. And the pattern here is that if you're looking at 2, 1, then in the first sum, you start from R3 dot dot dot. This 3 is the next number to 2. The second one, you start from S2 dot dot dot. So 2 is, of course, the next number to 1 minus Q times. Now you just take these numbers and you start at those R's and S's. So very simple and nice formula. And somehow this closes up into this nice, pretty product. So this is a conjecture. We don't really have a proof of this. Really, the only cases that are proved are the ones by Warnaar in the previous slide. Okay, so here is something that we were able to prove new. I just want to show you that, yes, we did some work. This is not just in the air. So this is a new identity at modulus 6. So you see a period 6 product here. And again, there is this annoying 1 over q to the infinity factor. So you don't actually get just the characters, principal character. You get this also one factor outside. And this is a new identity at mod 9. This is a new identity at mod 10. If you actually write out the full proof that we have for this mod 10 identity, it's a computer assisted proof. And I think if you print out the maple output, it goes into like 230 pages or something, but it's easily verifiable. Verification takes mere seconds, so it's not a problem. Finding the proof takes several hours. Okay, anyway, so all right, so now let me tell you how these things are proved, and I want to inch towards cylindric partitions and W algebras and whatnot. So cylindric partitions were first introduced by Gesell and Kratenthaler, I think in 1997, but I think they were somehow also implicit in the work of, I don't know how to pronounce his name. It's Burge, Burge, I don't know, who really essentially looked at like 2-row cylindric partitions. So the point is that they're Q generating functions. So they have a weight attached to them, just add all the parts. And their Q generating functions are exactly equal to the products in principal characters divided by Q infinity. So it's exactly that right-hand side. And this fact was almost proved by Gesell and Kratenthaler, except that they had to just use the McDonald identity to put it in this nice product form. And that is explained by Fora and Welch. But there is another paper by Borodin, and I think he's someone who works in integrable probability and something. So there is some other circle of ideas which also gives this. Now the point is that there is a way to soup up this generating function by introducing another variable called the maximum part statistic. It corresponds to this variable z. And now with this, you have nice recursions that govern these generating functions. These recursions are found by Cortiel and Welch. So what you do is you take our conjectural sum sites. At first, they were just the Q sum, but Ola Warnaar kindly told us that please introduce a Z. It's very easy to do so. And after you do that, there's going to be a nice generating function that comes about you, and then you just prove that your identities satisfy that generating function. So you do that plug in a Z appropriately, and you get that the recursion is satisfied in some low-level cases. You can prove that. And finally, you just set Z equal to 1 to get your sum and product identities, because ultimately our identities are just having Q in it. So there is no place for Z. All right, so that's the plan for the proof. I won't go wholly into the proof, but I will talk about now cylindric partitions and what all that has to do with W algebras and whatnot. So now my level of knowledge is going to negative infinity. So please ask questions, and I might not have all good answers. All right. So one thing I should mention is that are some sides with a Z introduced in there, they're not exactly equal to the ZQ generating functions for cylindric partitions. They are off by this factor. So this doesn't disturb the recurrence really, but these types of factors seem to be coming up a lot here and there. And so one question to ask would be, what are these sum sides then counting? If not, I mean, they are not just cylindric partitions, there is something else going on there. So I don't really know the answer. All right, so now let me tell you about cylindric partitions as I understand them. I don't understand them very fully. It's on the to-do list. Okay, so let's first understand partitions. I would hope that I understand that. So a partition is just a sequence of numbers, of course, non-negative. Sometimes you do need to put zeros, but at the moment we'll assume that this is all positive. And you organize them in your preferred order, either non-increasing, non-decreasing. It depends on which softwares you use. But think of this really as a linear partition. So you put boxes around that. Okay, sounds silly, but you will see that I'm going to put more boxes in future slides. So just do it at the moment. And if you really want, then you can think of this as a two-dimensional shape. So 7 boxes here, 4, 3, 2, 2, right? Okay, good enough. So partitions are linear partitions, but what we really want is, oh no, before that, I should tell you that really a linear partition is a lattice path. So you take this partition, and it's really a lattice path where you trace out this boundary of your Perez diagram. So this is 7, 4, 3, 2, 2, and this is the lattice path, right, at the boundary. Okay, so now let me tell you what a plane partition is. It's, instead of a linear partition, now it's a two-dimensional partition. So something like this. So you take a partition and you introduce numbers in there which are weakly decreasing and weakly decreasing in columns and rows. Okay. And you can put, you can think of these numbers as heights of boxes. So you can stack 7 boxes, 4 boxes, 3 boxes, and so on. And you get a 3-dimensional shape, which looks like that. And I found a nice program online written by Chang-Soo Kim, which produces nice, pretty pictures like this. So this is 7, 4, 3, 2, 2, and then 5, 4, 1, and 2, right? So that's what a plane partition is. And really, you should think of a plane partition as a non-intersecting lattice path. So there is, again, remember, partitions are lattice paths by tracing out a boundary. So plane partitions are going to be sets of lattice paths, one for each partition, one for each sort of a level in your plane partition. So this partition I told you, plane partition, how do you get a lattice path out of it? Well, first of all, pad everything with 0 so that you have a nice rectangular diagram. And now you just put each partition. So this, the first guy is 7 here, then 4 here, 3, 2, 2. The next guy, you put it a bit shifted. So this is 5, then 4, then 1, and these correspond to the 2 zeros. The next guy, you put it shifted again, so 2 and then 0. So by shifting, I mean you start at, you keep going to the northwest every time. So you shift their starting points and ending points, and you make sure that they end at exactly 1. So so really this partition should end here, but you just extend it so that it ends nicely to the northwest of this bullet here. Okay, and just the weakly decreasing condition tells you that these are non-intersecting lattice paths. Okay, so these are what plane partitions are. Equivalently, you can think of them as non-intersecting lattice paths. Now, McMahon, in way back in 1912, he already figured out what the generating function for plane partitions is. It's that. Okay, so it's 1 minus q to the n raised to n. Just partitions, you will delete this exponent n, right? Okay, but sort of the modern way to count, I actually don't know how McMahon proved this. I should go and read this. But the modern way to count these plane partitions is given by Gessel and Viennot, and I think their work had roots in the work of Lindstrom. So the point is you count all lattice paths, whether they are intersecting or not. So sort of like inclusion exclusion. And the only thing you say is that the paths have to start on the southwest corner of the bullets, and they have to end somewhere on the northeast bullets, but they might be intersecting or touching or whatever, right? So again, I'm only giving you the idea of how this is counted. I'm not giving you a full proof. But what you do is you count them along with a certain sign that they induce on the permutations of the starting and ending paths. So I'll explain to you what that means. So you count them with signs because you sort of want an inclusion exclusion type thinking there. And once you do that, you will see the while groups. I'm not saying group, I'm saying groups, because you really see all the while groups for all ends coming into the counting. Okay, so in this example, for example, so you are considering this 3-row type plane partition that corresponds to that should correspond to 3 paths, but this is intersecting, right? So this red guy intersects the blue guy touches the purple guy, right? So these are intersecting paths. We don't really want them, but they help us in counting. So we put them in our consideration. And now you see that these these paths are inducing a permutation of these bullets, right? The first path ends up on the second bullet. The second path ends up in the first bullet, right? So there is a permutation of 1, 2, 3 there. So what you do is you count these paths with the weight, but along with this sign of this permutation. Now what happens is that there is actually a nice involution on these set of paths where all the unwanted paths get paired up with another unwanted path, but with a negative sign. So there is a process that you do. So you see this intersecting lattice, path. So pick some sort of a convention that you pick the rightmost and the topmost intersection point. So that would be this here. And at that point, you reroute these paths. So the blue path will now go up and the red path will now go right. So you sort of reroute these paths and you still get a bad path. You still get a touching path, but I mean, here it was intersecting, but now it becomes a touching path, but it induces an opposite permutation, or rather a permutation with an opposite sign. And so if you do that, this is what I was explaining, you reroute them, then all the bad or unwanted paths, they get paired up with another one that differs in a sign in the permutation it induces. So they get all canceled out. So really, it's really no harm if you put in all these intersecting paths there, you still end up with the non-intersecting paths if you count properly. And now the sum over, the sum over signs is really interpreted as a sum over Sn, and then you evaluate the determinants that come in, and that finally gives you the formula for plane partitions.
Shashank,
yeah.
Doron explained this Gessel-Viennot trick once. I don't know if you were at this lecture. He said there's a big party and you want to know if there are more boys or more girls. So you clap your hands and each girl holds a boy's hand and they sit down and you see what's left over.
Exactly. So that's exactly what's happening. Yeah. So it's a very beautiful trick, and I'm embarrassed to admit here that I only learned it last year. Anyway. Okay, so what are cylindric partitions? So as I said, they were introduced by Gessel and Kratenthaler, and they were connected to the representation theory of SLR hat by Tingley in 2008. And I believe this is the earliest, but I'm not an expert in this. So if someone knows any earlier reference, I'll be happy to change these slides. But what he did was he understood the models for crystal bases for this using cylindric partitions. Okay, so what are these cylindric partitions? So I'll give you an example. So they are attached to profiles of these things where certain numbers in these profiles could be 0. And so this profile is connected, of course, to a certain module. So if you have a profile of length 3, then it is connected to SL3 hat corresponding to this module here. And what you do is you you take skew plane partitions. So forget this purple 762. So you take 3-row partitions, 3 rows because you have 3 entries in your profile, and you start reading it from right to left. So right, so first is 2, so you take the second guy shifted 2 units to the right. Next, you take the guy shifted 1 units to the right. And the last thing, what you do is you copy this 762 and put it above, shifted by 3 units to the right. Okay, so really the cylindric partition is just the bottom 3 rows that have white squares, but you do shift this 762, put it on top, and after doing this, you should still be weakly decreasing along rows and weakly decreasing along columns. So that's the condition, right? So when you count the weight, you only count the white boxes, but the condition really involves this sort of a repeated, sort of a repetition of you copy this, you put it on top, and so on. So really, you could continue doing this. Like now you put 653 on top, appropriately shifted, and you keep going. And so people like to draw this with sort of a cylindric shape that keeps winding up around itself. And the thing to remember is that the number of rows here is the rank that you have, so rank 3. And the total skewness, what is the total skewness? So the total skewness is how much 762 gets shifted ultimately. That's 6 units, right? 1, 2, 3, 4, 5, 6, and that's your level. Okay, so those are what cylindric partitions are. And somehow what happens is this repetition corresponds to the affine translations in your affine while group. And when you try to count them, this affine while group ends up controlling the counting. Just like before the finite while groups came into play, here the affine while group comes into play. And I admit that I haven't fully digested their proof, but this is roughly what happens. Okay. So the generating functions for these cylindric partitions, well, again, you count the total weight, and you also keep track of the maximum part in your cylindric partition. So here the maximum part would be 7. So this particular partition would get counted into z to the 7 q raised to whatever. So that's the generating function. And this is the object for which Courtille and Welch had their recursions. Okay, so we use the recursions that Courtille and Welch gave for this to do this. And that's not a new trick. That trick has been used by Courtille and Welch themselves for level 4 identities, and by Courtille, Dusa, and Unju for level 5 identities, and so on. So that's not really a new trick. Okay, so now let me explain the relationship to characters. And this is what I told you, that Borodin, Gessel, and Kratenthaler, and Fora and Welch, they did this really. So if you have this profile and you consider the generating function for cylindric partitions, but you put z equal to 1, then, so you forget this max part, then you get the principal characters of SL R hat modules divided by this 1 over q to the infinity. And if you don't want to think about principal characters, which means I'm only looking at the highest weight vectors with respect to principal Heisenberg, if you want to actually talk about the full modules, you can do that, but then this factor 1 over q to the infinity changes to this here, this factor. Basically, you have to account for the basic module in the denominator, and that's the correct factor to put in there. Okay, so this is how cylindric partitions are related to the characters. And this equality here, it was proved by these people. So the remaining part is getting the sum side for the cylindric partitions, and that's what we have been able to do. Okay, so one question I'll ask right off the bat is, what is then the representation theoretic meaning of this max part statistic? What is that counting? And we don't know yet. Okay, so these partitions have a really nice symmetry because of this sort of rotational, okay, not rotational, but
sorry, Shashank, could you just
yeah.
go back a couple of slides and
Yeah.
I missed Z is the max of pi. Okay.
Yeah, maximum part. Yeah.
So what does that, what is pi? Pi is a set of cylindrical partitions. Yeah. And what is max of pi? What does that mean?
Oh, it's just the maximum part. So 7 is the maximum part here.
I see.
Yeah.
I see. Okay. So you think of this. So I was thinking of it as a tableau, but okay, it's the biggest entry in there.
Oh, yeah, the biggest entry in there. Yeah.
Okay.
Yeah, the biggest height you get. Yes. Mm-hmm.
Okay, the height, yes. Okay, if you think of it.
Yeah.
Okay.
Yeah. Mm-hmm.
I mean, this affine action also shows up, I think, in first of all in my work with Friedrich Knopp.
Okay.
And then it is related, I think, also to Bogdan Ion's thesis, where he considers, I guess, just basic modules, so the character formula for basic module, and the de Mazur character formula, and how that specializes to how that's related to McDonald polynomials, which was also in the work of Yasmin Sanderson. So, I mean, some of these ideas are, maybe we should talk about them a bit.
Oh, definitely. I would love to. Yeah.
So it's very, very interesting.
Yeah. Yeah, so at the moment, we don't know what the interpretation is, but maybe, as you said, it might be buried somewhere in some paper somewhere, but we'll have to think. Yeah. Okay. So because of this sort of a recursive nature where you're taking off the bottom row and putting it on top, right? Because of this, pretty much by definition, these cylindric partitions have nice rotational symmetry where you put this CR first, and right. So you think of these as infinite sets of rows, each shifted right, and really it doesn't matter where you start counting. Yeah, so they have this nice symmetry. But they also have other symmetry. So if you set this Z equal to 1, then you should also be able to see the Dinkin diagram symmetry of just, I mean, the characters have this outer automorphism symmetry, right? If the principal characters, I mean, because you're specializing, after all the e to the alpha i's to just a single thing, q. So there is really no difference if you have a automorphism of the Dinkin diagram. And that's what you're seeing here. If I reflect all these c's, then I should again get a symmetry, but then you have to set Z equal to 1. So if you set Z equal to 1, you have the full dihedral symmetry of the Dinkin diagram, but if you actually have the Z in there, you only get the rotational symmetry. So I don't know if that says anything about where to find this interpretation of Z in representation theory, but probably it could help. That's the reason I wanted to mention this. Question? Okay, maybe not. So I'll, in the last 3 minutes or so, or 4 minutes, I'll tell you what this has to do with W algebras. So there is a process starting with a finite simple Lie algebra and a nilpotent element in there and a level. There is a recipe to start from the Verma module VOA, and there is a functor. It's called Drinfeld-Sokolov reduction functor, and you get this W algebra there. So this dashed arrow means it's a functor, it's not a homomorphism. And typically this is not simple. So you can also consider it simple quotient. Now this is going to get confusing in a bit because at the moment I'm taking the level as the subscript, but soon I'm going to take the rank of G as the subscript, and I'm going to take G to be just type A. So if it gets confusing, just do ask me in a bit. So these principal W algebras come from the principal nilpotent element. And I'm really looking at these SLN type W algebras, and I'm looking at the W algebras that come from the reduction at some very specific kinds of levels. And so you also designate these algebras corresponding to these levels by these numbers P and Q. Okay, that's just the designation of what these algebras are. It doesn't matter a whole lot at the moment.
Sorry, could you just back up one slide?
Yeah.
I missed the definition of,
yeah. Which one?
Okay, you didn't define the W.
No, I didn't define.
Okay, I thought you defined it. Okay,
I don't think I'm competent enough to define that. This is actually yeah, it's not a part of, yeah, I haven't learned this very properly. Let me say it that way. But there is a reduction functor, and it gives you some W algebras, which are vertex operator algebras, but they are not as simple as the Lie algebras, like the VOA is built out of Lie algebras. Anyway, I have worked on them a little bit, but not as much as I would have liked, let me say. Okay, so if you look at SL2, then what you get are Virasoro algebras and PP prime. So we of course understand the combinatorics of that, at least when you put P equal to 2, that gives rise to Gordon-Andrews identities and so on. And for general PP prime, the combinatorics was understood by Welch. So he really did that. And the fact is that the set of principal characters of SLN hat at level L is related to the set of characters of this W algebra at these parameters. At the moment, it's not going to matter what these parameters are. But the condition you have to put is that this N and L has to be co-prime. Otherwise, something goes wrong in the definition of these W algebras. So that's another relation. And really, our work talks about W3 algebra at these parameters. Okay. And so this is also related to the cylindric partitions. I'll skip that at the moment. You can believe it already because principal characters of SLN hat were related to cylindric partitions and they are related to W algebra. So there is some relation. But now in the last 2 minutes, instead of taking, so at the beginning of the talk, I took level to infinity limit. Now let's consider rank going to infinity limit. And so instead of Wn algebras, you think about W infinity algebras. These were constructed by my colleague, Andy Linshaw. And the finite Wn algebras they are truncations of W infinity. I shouldn't say finite W algebras. That's actually a whole different thing. I mean, coming from finite ranks, that's what I mean. And if you see the character of this W infinity object, it is very similar to the plane partition, but it is off by 1 in every coordinate, right? So really it is off by Q infinity, which you have seen this factor now. It always is there lurking behind in all our identities. And really the way to understand it is that it's the character of rank 1 Heisenberg VOA. So physicists, what they do is they tensor this W infinity with Heisenberg. They get this thing called W1 plus infinity. This is really what is related to plane partitions. And now when you truncate the plane partitions, you get cylindric partitions, or other way of saying that is cylindric partitions with infinitely many rows are really plane partitions because you lose that rotational symmetry if you have infinitely many rows. All right, so that's really the last slide. I don't know why Heisenberg makes life easier, but somehow people tend to like this W1 plus infinity algebra a lot more than W infinity. It is easier to play with. I don't know if there is actually I do know that there is an explicit way to relate the combinatorics. There is a paper of Prochaska which relates this combinatorics of W algebras to cylindric partitions, but I actually don't remember how much rigorously proved. So this is something for me to learn. This W infinity has other truncations, not just the WNs. So you have other VOAs coming up as truncations. What are the combinatorics of those? And lastly, I have no clue what happens in type B, C, and D. So I have this object with Andy Linshaw, which deals with the W algebras there, but I don't think anyone knows the combinatorics of this object, what it deals with. So that's it. I think I went over time. But...
So, thanks so much. Shashank, I have a question.
Yeah.
A long time ago, when I was discovering my numerator formula,
yeah,
I noticed that the principal specialization of McDonald's identity for, I think it was SLN, gave a recursion generalizing and analogous to Euler's recursion for P of n but for using McMahon's formula for K-road plane partitions.
Oh,
And that's Alex, who's here, remembers how we were thinking about all such things. And this preceded how the principally specialized characters could be involved. Well, the fudge factor, which is the principally specialized character of the basic module, and it preceded all of that. It was before vertex operators, and it's just a long shot guess, but I was, since I'm home and I'm at a laptop, I could print out my paper, application of the numerator formula to K-road plane partitions, advances 1980. And I couldn't tell whether what you're doing it could be indirectly related to that.
it must be. I should read that paper.
There isn't much in it. It was an excuse to publish my numerator formula.
Don't go.
So maybe that's related.
Oh,
but
yeah.
it's related, to it was preceded the discovery of the fudge factor and all that stuff. The dividing by the principally specialized character of the level 1 standard module story. So it's part of that circle of ideas. So maybe it's related.
Yeah.
And also I was going to say, so far you don't see intrinsic representation theoretic phenomena for the sum sides, or your.
Yeah, we don't. I don't know how, like, if you did your Z algebra stuff, I have no clue how cylindric partitions are supposed to come out of it.
So, questions, people?
Yeah, I can. Yeah, I mean, I can ramble on about this Bailey thing if you're interested.
Yeah, I'm interested, right? So
I don't understand it fully, and my understanding comes from actually, in fact, knot theory papers. So what happens is, if you have a knot, then for every finite representation of SL2, you get the Jones polynomial, right? So associated to every knot, you have a sequence of polynomials. And the question is, can you find some sort of an element in the quantum group such that, associated to this knot, such that if you evaluate that element at the SL2 representation, you recover this Jones polynomial. Okay.
You mean its trace or something? What does it mean to evaluate an element?
Yeah, so it's in the center of So
it's a central element.
Yeah.
Okay.
So right, so it will give rise to some polynomial if you evaluate it on a representation. And the question is, given a knot, you have the sequence of polynomials and then the question is, can you find this element in the center of the quantum group, right?
I see.
Now, I think Habiro, he gave some basis for this center of SL2 quantum group. Okay. And it's not exactly quantum group.
So is it just SL2 or it's not affine SL2?
It's just SL2, UQ-SL2.
Okay.
And he gave a canonical basis for this center. And the point is then in this, not the center, I think it is some completion or something like that. Okay. And the point is then, in this completion, can you relate the Jones polynomial to some element, right? And the relation between what you get as the Jones polynomial and this element in the center, that's exactly the Bailey relation. So in particular, it is independent of the knot. So if you know the Jones polynomials, you can find out this element in the center and vice versa.
Oh, okay.
And this relation is exactly Bailey relation at A equal to Q squared or something like that.
Where is this? Where did you learn this from?
So you're asking for trade secrets.
Oh, trade secrets.
No. No, it's not me. So there is two papers really. One is a paper of Hikami and Lovejoy, where they actually say what the cyclotomic expansion of Habiro has to do with Bailey pairs. And then there is a paper of Gorsky and Belyakova, recent paper, where they want to sort of do this for all SLNs.
Okay.
So if this is related to like a knot theory,
yeah,
then
sorry, just one second. Can
yeah.
Is this the paper on?
I'm going to stop recording.
Yeah.
Oh, okay. Is this the paper on